Pictured below is the velocity versus time graph of an object that holds different constant velocities for different time intervals. It's a piecewise-defined function where the velocity remains 1 meter per second before t equals 4, and then it jumps to 3 meters per second at t equals 4. So this function has a discontinuity at 4 seconds. And say we wanted to do a definite integral of this situation. Technically, we're not supposed to integrate over a discontinuity. However, it is valid to break a definite integral up into two definite integrals using the formula shown here. So first of all, let's try to do the definite integral for going from t equals 0 to t equals 6. The area under the curve is as follows. And all we're going to do is split it up at this point where the discontinuity occurs. So we'll go from t equals 0 to 4, and then we'll do a separate integral from 4 to 6. The definite integral that we're interested in is going from 0 to 6 of the velocity function. However, because of the discontinuity, we're going to break it up into two parts. We'll go from 0 to 4, and then we'll add another integral from 4 to 6. Now, why is this useful? Because the velocity actually follows different formulas on these different intervals. So we can plug in the formulas. At first, the velocity is 1. And later, it jumps to 3. We'll want to evaluate each of these. The antiderivative of 1 is going to be t. And we need to evaluate that from 0 to 4. And then we want to find an antiderivative of 3. That's going to be 3t. And we'll go from 4 to 6. All right, now I want to take that t, and using the fundamental theorem of calculus, I want to subtract, I want to plug in the 4 first, and then the 0. And I'll do the same thing over here for the 3t. We'll get 3 times 6 minus 3 times 4. That's going to give us 4 plus 18 minus 12, which is 10. All right, we just want to check to make sure that the answer we got actually matches up with the area under the curve. So if we count the boxes here, let's see. We've got 6 boxes in this section and 4 boxes in this section. So it's true. Yeah, the area under the curve actually is 10. But what's new here is this is an application of integration, and the 10 has units in this case. So what would be the units? Well, we had a velocity function, which has the units of meters per second, and time has the units of seconds. Now when you multiply meters per second times seconds, what do you get? Well, meters. These seconds will cancel. And the question is, what does this mean? Well, the 10 meters is going to be what is called a displacement. It's a change in position. So this is going to be a displacement of the object. Let's go back and see if we can construct a position versus time graph for this problem. And then we'll see the meaning of the 10 meters. Some information about the position is given in the next line. It says that assume at t equals 0, the object is located at an x of 0. So we want our object to start off here. That's going to be our object's position at time t equals 0. We want to show where the object goes from there, remembering that velocity is the derivative of position, and so the position will be the antiderivative of the velocity graph. So the way that we'll draw the curve is to actually integrate the velocity functions. We'll do an integral of 3 dt as well as an integral of 1 dt. This is because the velocity is 1 meter per second to the left of 4, and it's 3 meters per second to the right of 4. All right, so what do we get if we do those antiderivatives? We'll get 3t plus some constant. And here we'll just get t plus another constant. Now, from the information given, I can actually find that first constant c1 pretty easily. It's going to be 0. That's because during this interval, they had said the object would be located at an x of 0 at t equals 0. So we're going to want t plus 0 whenever the time is less than 4. That'll be the function that it follows. But then an important change happens in the motion. At t equals 4, the slope changes. It changes from a 1 to a 3. But what constant do we need to attach there? Well, we should actually use algebra to figure that out. We know that our graph has to touch the point 4, 4. So what I'm going to do is I'm going to say x equals 3t plus c2. I'll plug in this combination of t and x. And now I have to solve for c2. c2 is negative 8. And that's what goes there. So all we have to do is now draw a line with a steeper slope. And we'll have that. All right, so where does the 10 meters come into play here? Down below, we had said that if you integrate from 0 to 6, you get a delta x of 10 meters. It's a change in position. So what we want to verify is that when we start off here at an x of 0 and end up 6 seconds later at a new position, question is, how far have we actually traveled? The answer is 10 meters. What this shows is that the area under the derivative curve tells you the change in the value of the antiderivative curve. The delta x of 10 means we went up. We went up 10 units. Now, how do we state this in calculus? With the fundamental theorem. The integral from a to b of a function equals the change in its antiderivative function. Another way of saying this is delta f from a to b is equal to the integral from a to b of little f. Both of these statements say the same thing.